Okay. Good afternoon, everyone. So today we'll be going to brush up some math concepts which will be helpful for following the coming lectures of uh, this course. So we'll begin with defining a function. So what's a function? Function is a relationship between two quantities which defines how a quantity varies with respect to another quantity. So, for example, a function relates to an output, and a function is not just a relationship. Uh, it's specific in a sense that it relates each element in a set or set into an exactly one element in another set. For example, here you can see two relationships, and can someone identify which of these is a function?
The one on the left is a function.
Yeah, that's correct. Because all of the elements in the x has an image in the y, and all of the elements has only one image in the range or in the coordinate. So in the right relation, you can see that the 3 and 4 elements of the x set has no image in this y set, so it's not a function. And before we begin, can we just think of what all functions would be there in ecological and biological systems? So I have jotted on 3 biological phenomena here. So can someone suggest what would be the independent variable and dependent variable for this phenomena? So for
birth and
sorry.
Birth or dependent variable?
Age can be independent variable.
Yeah, but so independent variables, yeah, so we can have any set of dependent and independent variables. So the only thing is the independent variable should not be the dependent variable should be depending on the independent variable, and there should not be any other dependency for the independent variable. So can someone so if we consider growth, can someone identify what would be the dependent variable?
Population size.
Yeah, population size would be one. Anything else? So what would be the independent variable which affects the population size?
Time.
Yeah, time obviously would be one independent variable. Yeah, we can think of multiple independent variables. Like even for competition, you can someone suggest what would be?
Resources will be independent variable in this case.
Resources can be, yeah. So the variable which it affects would be
Population.
Yeah, competition itself.
Yeah, competition would have some effects on the population. So can you identify what would be that variable which
The growth rate of one population versus another.
can growth rate can be and we can have, yeah, we can here also we can think of time as an independent variable if, yeah, over time the competition changes. Yeah,
Space, availability of space.
yeah, availability of space also, I think we can yeah, can be something dependent of resource.
Foraging, resources again for foraging also would be.
Yeah. Resources could be an independent variable. And what would be the dependent variable for?
Per capita food intake.
Yeah. Yeah, per capita food intake, or we can term it as foraging rate or something.
Population size can also be an independent variable in competition.
Yeah, sure. Population size or the population density, like, yeah, it can be an independent variable. Yeah, so we can.
I have a question. So, with increase in population size or growth, also the resources are depleted faster, right? So, I'm like, can resources be a completely independent variable, or like if it's the quantity of resources with increase in population, resources will be depleting faster? Right?
Yeah, that's a important question. So, so if the resources itself is dependent on the growth rate of the organism or the dependent variable, then we can't uh, construct a function based on this too. So the one of the changes that we could make would be the carrying capacity of for the so if the so the carrying capacity would be independent of time for a per population. So if we change the resources to be the carrying capacity, the changes in the carrying capacity would in turn would be affecting the growth rate or the resource intake of the organism, which we can construct as a function independent of time. Yeah. So we can think of many such ecological phenomena which we can which we can represent in terms of function, and yeah, we can come back to this diagram later and think of what would be the function which will be these different kinds of relations following. So for now, let's think of when we see a function, what all intuitions we can make out of it. So when we have a function, we can see what type of function is it, whether it's polynomial, trigonometric, exponential, or something. And we can think of the domain and range of that function. And we can get the key points of that function, like roots, maxima, and minima. And you can see how that function is changing in different intervals, what are the slopes of that function, and what are the rate of changes of that function, and how is that function increasing or decreasing in different intervals. And using all this intuition, we can draw that function. So in this tutorial, we'll be addressing all these points. So to begin with, what's the domain and range of a function? The domain is a set of elements over which the function has defined output. And range is the set of outputs that the function can generate. So for example, here, this function is from x, is defined from x to y. So the domain of the function is x. So you can see it's a set of 1, 2, and 3. And the function is defined from x to y. So y is the codomain of the function. So it's a set A, B, C, D. But you can see the range of the function is not same as the codomain. So here the range of the function is set of C and D. So So yeah, so here the domain of the function is x, set x, and the range is set c and d. So now we can think of yeah. So you can see the screen now.
Yes, yes, we can see.
So here we have three different functions. So can people suggest what are the domains and ranges of all these different functions? First, we can see y is equal to sine of x. So can someone suggest what would
Domain
be?
is from -infinity to +infinity and range is from -1 to 1.
Yes, correct. Let me write it down. So yeah. So pardon with me, I am trying this gadgets out, so my handwriting will be really bad. Yeah, so the domain will be set of minus infinity to infinity, or it would be the set of real numbers, and the range would be set of -1 to 1. Maybe can someone quickly suggest what would be the range for exponential and logistic functions? So here, here you can see the range would be
Range, the domain would be again from -infinity to infinity, and range would be open bracket 0 to close bracket infinity.
yeah.
Sorry, open bracket infinity.
Yeah, I'm not sure of this notation, but I think it should be fine. Yeah. So similarly for this logistic function, can someone? So this natural logarithm, it would be the reverse of exponential function. So it will be from 0 to infinity, that domain, and the range would be from no, I made no, yeah. So it's quite possible that I would make some stupid mistakes. So if people found something, just intervene. Yeah. So similarly, you can quickly think of the domain and range for y equal to x cube. So it will be from from real numbers to real numbers. Yeah. Okay. So coming back to so when we think of the roots of a function, it's the points at which the function is equal to 0, like f of x is equal to 0. So for different functions, we can think of the roots, like for x square it will be 0, 0, and for x minus 1 you can see that it's 1, 0, and for x square minus 4 you can see that we change this this function 1 to make this function 3, and we got two roots now. We can you can see graphically this roots of the functions will be the points where the graph crosses the x equal to 0 line. So at this point, the value of the function will be 0. It can be looked into as the solution for the function, or when the function is equal to 0. Slope of a function. So do anyone have any question to this point? If there is anything to be clarified or anything to be added by anyone, please, let me know.
Can you go back to the domain range kind of that graphs? I didn't get why y equal to x cube is. I don't understand that part.
Yeah. So here you can see. So you can see for which all x values you have an image. Like so here the domain will be the set of x. No. So you can see for which all values of h values of x you can have an image in y. So
Basically, all real numbers are both the domain and the range, right?
so for any real number, so for any x value belongs to R, a real number, you can get a corresponding x cube, and you can map it into the corresponding y. You can see it will be belonging to real values, and you can see it by if you once you have the domain, you can see how so it will be set of minus infinity to infinity. So you can see when limit extends to minus infinity, where y is going. So it will be for x cube, it will be minus infinity itself. And for similarly, for limit extends to infinity, y will be tending to infinity. So here you can see for x belongs to R, y is also belongs to R. So the domain and range of this function will be a set of real numbers. Right.
Thanks.
Okay. So the slope of function is the average rate of change of function in an interval. So slope is defined in an interval a b. So it will be the change in f of b in that interval divided by the change in x. Basically, if you define the function to be y, delta y by delta x. So a function will be increasing if the slope is positive, and the function will be decreasing if the slope is negative. So we can think of this slope in a really small interval. When this interval AB is really small and it's really infinitesimally small, this can be called as a derivative of the function, which is ds of x divided by dx, or dy by dx. So this derivative of the function denotes the rate of change of that variable with respect to the change in another variable at a particular value. And this derivative will be the slope of the curve of that function at that particular point. So here you can see for this function, you can define a particular interval and get the difference of f of x and f of y, f of a and f of b. So if this is a and this is b, so this will be f of this will be f of a, this will be f of b, and the slope would be this difference divided by this difference, which will be the slope of this line, basically. So if you think of reducing this interval further and getting it really close to this point, or any point for that matter, the slope of this line would be the tangent to that point. Here, if you construct the derivative or the slope of such interval, it would be the tangent to this curve at that point. So this so the slope of this line will be dy by dx, or the derivative of the curve at that point. So stop me if anyone has any doubt or anything to be clarified. Yeah, so these are the common derivatives for different functions. So I will be sharing this slides with all of you, so you can have a look at them later. So most of these things we would have been studied in the 12th class or something. Yeah. So the maxima and minima, the extremas of a function, will be the points where this derivative is equal to 0, which implies the function is not changed. The rate of change of the function, the variable y with respect to x, is 0 at that point, or the variable y is not changing with respect to x. So can we identify which all will be the extremas for this function here? So can someone say how many extremas we have here?
2.
Still 2 or more?
3.
2.
5 extremas.
Okay. Someone said 2.
3.
4.
Someone said 4. So I think 4 is the correct answer, as there are, you can see 4. You can see 4 such points in this curve. So you can solve this 4 points, have derivative 0. So you can essentially draw a tangent which is parallel to the x-axis. So the slope of the tangent will be 0, which says the derivative of that function is 0 at that point. So there are 4 such points here. So this function has 4 extrema. So the local maximas will be the extrema where the neighboring points are less than the extremum point. So suppose if C is the extrema point, all the x which are nearby in a neighborhood of value h will be greater than or equal to sorry, it's actually the other way. It's correct. Yeah. So f of c will be greater than or equal to all the f of x which are in a neighborhood of h. Similarly, for local minima, all the neighboring values will be higher than the extrema point. So here you can see there are 2 local maximum for this function, and there are 1 local minimum. And we can without looking into the graph, we can find out whether the function, whether the extrema is a maxima or minima by computing the double derivative of that function. So if we have the double derivative of the function at that point, if the double derivative is less than 0, it will be a local maxima. If it's greater than 0, it will be a local minima. I can explain this in more detail using graph. So here you can, so I think people can identify which all are the local maxima, local minima. So these these 2 points are local
maxima.
And maybe I will give another notation.
Other color.
Oh, yeah. And these 2 points are local minima.
Local minima.
So if you think of taking another derivative of this function at that point, so let me focus on this region as it's much less cluttered. If you think of taking the derivative here, you can see the derivative will be 0 at this point. And prior to this point, the function is decreasing. So the rate of change of y with respect to x is negative. So, people understood it, right? So we can qualitatively say the rate of the dx, the derivative of the function is negative at this region, and in this interval, you can see the function is increasing with the value of y is increasing with respect to x, and it's so it will be positive. And at this point, the derivative is 0, so it will be at 0. So essentially, this line would represent dy by dx. So taking another derivative of this function would mean taking another derivative of this itself, which implies it's the slope of this line. So this line is the derivative. So that line represents dy by dx. So so d by dx of this line will be the slope of this line. So it will be so it's positive. So it will be a positive value, and we can so you can see it will be a positive value. And similarly, for a maxima, it will be the other way. So suppose for this maxima, you can see the dy by dx will be a line with negative slope. So the second derivative will be a negative value. So thereby we can see that if we identified a extrema and we could calculate the double derivative and see it's negative, it will be a local maxima, and if it's positive, it will be local minima. Is there anyone who need to explain this more? Or
the saddle point is something different, is it?
Sorry?
The saddle point, what is saddle point? That is next.
So for saddle point, we'll get this. So here I don't have a saddle point. So for saddle point, we'll be getting essentially this line to be 0. So the dy by dx will be the double derivative. The dy by dx will be line 0, or not necessarily 0, but a line with slope 0. So at a saddle point, so the function is increasing, but it becomes the derivative becomes 0 and it starts to increase again.
Okay.
So the so here okay, I think I made some so the function, so for this particular saddle point, the dy by dx will be something like this. So the first derivative is positive and it becomes 0, and it again starts to increase after the saddle point. So so at this particular saddle point, if we get the double derivative, it will be the slope at this point and it will be 0. So we can't conclude whether it's
Extrema or
so if we get the 0, it will be a saddle point.
saddle point. Okay, got it. Thanks.
So continuity of a function. So naively we can say that a function would be continuous if we can draw the function without raising our pen from the paper. So essentially, which means that the function f of x is continuous at a point c if the limit extends to f of x is equal to f of c, which implies the at a point c, the image of that function is equal to f of c, I can explain this better in the next slide. So a differentiable function is a function whose derivative exists at each point on its domain. So all functions which are differentiable. So if a function is differentiable at a point, it will be continuous as well. But for a continuous function, suppose here y equal to mod x is a continuous function, but it is not differentiable at point 0. And here you can see a piecewise function which has a break at point x0, so which is discontinuous. So here you can see this two parts of this function is defined using two different pieces. So here the f of c, which is defined by this part of the function, will be this point. So can you see my mouse cursor?
Yes. You can use that pointer, so that in the.
I don't know how I can access. Yeah, maybe I will. Yeah, I will go with the mouse pointer. Yeah. So here the f of c predicted by this part of the function will be this point, and the f of c predicted by this part of the function will be this point. So at this point x0, when we consider an interval around when we approach from negative negative side of x0 and positive side of x0, we will get two different f of c values at this point. So limit f of c tends to f of x tends to c, will we won't get the same value, or we won't get f of c. So at this point it's discontinuous. By graphically, you can see if see a function to be discontinuous if it has some weight in its curve. And
practically, how can such a thing happen? I mean, discontinued.
So think of a biological system. It could be there could be some threshold behavior. After some threshold, an organism starts to show some behavior. So the y-axis is some response of that behavior. We won't see the response, or we won't see an elevated response until this point. And after that point, after the system crosses that threshold, we will start seeing an elevated or a different kind of response. So in a biological context, it could be some threshold kind of response.
Okay, understood. Thank you.
Yeah. So to understand differentiability better, so suppose this is the function that we considered in the previous example. F of x is equal to mod x. So at this point, from our definition, the derivative of the function was the slope, can be said to be the slope of the tangent to that point. So here we can draw many tangents to the point as it's a sharp, or it's a sharp point or something, like the slope changes abruptly, so the derivative of the function is not defined at that point. So even though this function is continuous, it's not differentiable at the origin, at the point 0. Yeah.
Shuaib, sorry, could you repeat that part?
Yeah. So you understood about the derivative of function at a point, no? So we defined it to be so if suppose it, so we have to find the slope at this point. It would be the derivative of at this point. It would be the slope of this line. So if the function doesn't have a well-defined tangent at that point, we can so I'm saying this in a graphical sense. So if we can draw multiple tangents at that point, it doesn't have a well-defined a well-defined slope at that point, so it doesn't have derivative. So it's essentially not differentiable at that point.
Okay, got it. Thanks.
So now we can think of, if we have a function, what transitions can we make to that function? So suppose if we have a function f of x, we can make transitions to that function to make another function g of x. So we can try applying this to now. Yeah. So suppose this is our function f of x. and we are transitioning it into two different functions. So you can think of how f of x minus a would be transitioning the function. So f of x of a, you can think of f of x minus a, this as a map from this as a function where x first maps to x minus a. So a point, if we consider the origin, 0 will be mapping to minus a. So the image of minus a will be the new or the current image of 0. So if we think of it, so 0 has an image here, is some negative, some negative value. And if we, for simplicity, if we assume a to be this point and its image is 0. So the current, so if we apply this transition, the new curve will have 0 to be the image of 0, as a as 0 was the image of minus a for the original curve. So just simply applying this transition will make this curve to move like this. And now if you think of applying this part, adding a constant to the function f of x minus a, this will essentially be transitioning the function in y-axis as it's applied onto the f of x value. So if you think of it, now this this function will be mapping, if you consider the point 0, it will be mapping the image of 0 to point 0 plus b. So if you consider this to be, the image will be the original image was 0. The new image will be y plus b. Okay, so you can see this curve will be shifted upward by b. And this this transition will be by an amount of a. Yeah. And now if you think of the transition g of x equal to 3 into f of x, and here also the transition is applied at the y-axis as it's applied after applying the function f of x. So y would become y into c. So essentially you can, so if this was the original function, the current function, all the points will have an c into y transition, which will
so here c is a constant.
yeah.
Okay.
So no, so I made a mistake. Yeah, so the transition would make the y value can someone think of what would be the transition?
Won't it just get like a broader curve?
Yeah, that's what I think. But I'm
All the
thinking
values would be multiplied by 3 now. For all values of y would be multiplied by 3 for every value of x, which was there originally. So,
So it
sorry,
will just
multiply
move
by
up much
c.
higher.
Multiplied by c, sorry.
Yeah, it'll be the same as like addition, except it will move much higher. The change in the curve will be much higher than say simple addition.
so this would be the transition curve, no? So for negative values, it would
Yes,
make
sir.
the negative. For positive, it would make further positive.
But
Yeah.
that point can't change. Yeah, that is correct. That is the difference between the previous one and this thing, right?
I think at the point f of x equal to 0, it won't change, right? So it
Yes,
would
yes,
be
that's right. Yeah.
so it would be crossing this line. So I
It
made
should be crossing. Yeah, that's the difference between the previous function and this function as well.
crossing this line, which would essentially be something like this. Yeah. No? Yeah, I think. Yeah, I think this is correct. If I will check this, and if it's wrong, I will. Yeah, do that. But yeah, so it would all negative values will become further negative, and it will be crossing through this point. Yeah. No. It's actually the other way. So sorry, messing this up. So I think it would be like this. So y is positive all for all this question. So assuming c to be a positive constant, all these values would become much more positive, and all these values will become much more negative, and here it won't change. Yeah, so it will actually elongate the function in y-axis. Yeah, I think this is correct, and I messed up before. Okay, if anyone find anything wrong, yeah. Okay, so I think it's correct. Yeah, so if we can understand the transition happening to your function, we can find the change in domain and range for a function. For example, if we consider this function 2 minus square root of x minus 3, and you can see.
Transition or translation? I mean, translation. I mean, it's.
Oh, I think it's translation. Sorry. Yeah, I think both can be used. I'm not sure, but yeah. Yeah, so if you see, if we do different translations to a function, it will change the domain and range accordingly. Yeah, so you can see this function and see how the domain and range are changing. So should we work this out, or can you guys do this later? I think I would keep it for now. Yeah. So now we can think of how, if we get a function, how we go ahead with plotting that function. So keeping in mind the concept that we learned till now, so what would be the first thing that we'll be looking into in this function to plot it in a paper or anything? So what would be the first thing that we could get out of this function to help us in plotting this function? Can someone suggest?
The roots of a function.
Yeah, the roots would be one. Yeah, first thing that we can get out of this function. Then I think we can go ahead by calculating the root and see what are these. So can someone quickly calculate the root of this function? Okay, anyone can. Yeah, everyone can do the same. So we'll be essentially getting yeah. 50. The root would mean we equating y is equal to 0, and if someone has done it, can you update it, or I have already calculated it, or I can, if you calculating, they can do by their own. So the
X would be 0 and x cube. X would be 4 and x cube would be 0.
yeah,
I think.
4 and 0 would be one root, and if you think of it, 0 and 0 will be another root. If you 0 and 0 will be the trivial root, isn't it? If you give 0 to this equation, you will get 0. So we got 2 points in the curve, 0, 0, and 4, 0. So these are the two initial informations we get out of the function. Okay. So what would be the next step that we'll be taking? Any suggestion? So it would be the getting the derivative and seeing which are, and essentially getting the extrema. So if so this will be root. Now if we calculate dy by dx, it will be 4x cubed minus 12 square and at extremas, this function will be 0. And similar to what you did for solving for root, you can do to get the maxima and minima, and people can do this by their own and update me after you finish.
$12x square minus 24x dy by dx, if you differentiate that equation.
Yeah, did you solve for the extrema?
No, not yet.
Yeah.
Shoaib,
Yeah.
so you take a second derivative of this equation, and then how do you solve for the extrema? What do you do?
Yeah. So now we for getting the extrema, we got the first derivative. So it is this, and we equate it to 0 and solve, and we will so the solutions that we get for it would be the extrema, and then we can take the second derivative and see if the values of second derivative is positive or negative, and which will inform us about whether the extremas are minima or maxima. So
Okay, fine. All right.
It is 0 and 3, right?
Yeah. Yeah. So the extremas will be 0, 0, and 3, 3 and minus 27, right? So if we so we'll get so by solving this equation we'll get that extremas to be 0, 0, and 3 and minus 27. So we will get 0 and 3 to be the roots from this equation. So if we substitute 3 to this function, we will get the corresponding y value. So it will be minus 27. So we got an additional information here. So the one extrema will be 3 and minus 27. So let's see somewhere here. So now if we get the double derivative, which is essentially and this is the double derivative, and if we substitute the extrema points to this and see if it's positive or negative, we'll get the information of whether the extremas are maxima or minima.
So 0, 0 seems to be a point of inflection instead of an extrema, right?
With this saddle point.
Yeah.
So we
And
can, and you will see this point to be a minima if you substitute 3 and minus 25.
Yeah.
So we get some idea of this function. So we got the function to have a minima here, and the logical thing to do would be to connect it and connect it and yeah. Suppose this is the minima, we could just connect it here and here, and this would be a saddle point. And now we can think of what would be happening when this function is approaching minus infinity and infinity. So now we can think of the domain and range of this function. So the domain we can get from the first instance itself. It's the set of real numbers. And now as we come to the minimum point of this function, we can get the range of the function as well. So the domain of the function will be R, and range will be from minus 27 to infinity. So when
So, isn't infinity always written in open bracket, since you cannot exactly reach that point?
I think then mathematical notation is to use close bracket. I think it's close bracket is the correct usage, but I'm not sure. I think close bracket is the correct usage. No, yeah, close bracket is the correct usage, I think. But yeah, I'm not sure of the rationale behind it. Yeah, so the only thing that we want to see now, how this function behaves when the system is tending to minus infinity and plus infinity in the domain. So when the function is increasing along x-axis and minus x-axis. So we can see this by looking into the limits of y. Limit of x tends to the extreme value minus infinity. What would happen to the y value? So here you can, if you solve it,
won't it also go towards infinity if x is it's we consider x to be infinity minus infinity? It should also go to minus infinity, right?
Mm, yeah, so the both x raised to 4 and x raised to 3, if we consider the positive x-axis, both x raised to 4 and x raised to 3 will be increasing when x is increasing, but x will be increasing much at a higher rate than x raised to 3. So when x tends to infinity, y will be tending to infinity. So we can say when x tends to infinity, y will also be tending to infinity. Positive, which implies this will be increasing when x is increasing. Similarly, we can consider for minus infinity. Similarly, we will see x raised to 4 will be positive and it will be increasing, and x raised to 3 will be negative, but as it's minus 4x cubed, it will make the whole function to be positive. So it will also be increasing, which implies x tends to minus infinity, y will also be tending to infinity. So this will be a crude way to plot this function by capturing all the qualitative features of this function. So the things that we did is we first calculated the roots, then we found out the extreme points and whether it's maxima or minima by getting the double derivative at that point. Then we looked at how the function is changing at the limits of the domain when x is tending to the limits, how y is behaving, and this helped us to plot the function. So I think now we can take a break and people can work out with this function and see whether they can plot these functions qualitatively, and maybe we can come after some time and see how the functions look like. So I think I think we can. I will put this screen to be shared, and for how long we should break. I think who all finished doing
Shuaib, you're muted.
Sorry. Yeah. So I think yeah. So I will share that screen, and people can work out by their own. And once they can finish all of them, they can put their hand up. And after I see some sufficient number of hands, I think we can resume and see how those functions look like. And maybe after that discussion, we can discuss it. Does it sound okay? So I will.
There's another session that Vishu just mailed about that useful for CES people right now. So can we meet like later?
Okay. So when is it happening?
It's happening now till 5.
Okay. So then, yeah, then I think I almost finished now. So I will share this presentation, and people can work out these functions by their own, and maybe get back to me. And yeah. So if people want to attend that session, maybe we can discuss now. What others think?
Can you show those functions again just for a minute? So once we are done with it, should we send a mail or something to confirm the answers, or what?
Yeah, maybe you can. You can work this out and plot it in a paper or something, and send me the picture.
Okay.
I think I had something more. Maybe we can meet for half an hour or something later. If people want to attend the other session now, we can disperse for now, and if we can work out this, then we can have a short meeting maybe tomorrow or something. If it sounds good.
Yeah, sure. I think that will work.
What would be there in discussion for tomorrow?
So we will we'll discuss about how which all will be the common function types will be present in the ecological systems, and how we can graphically represent them and all.
Okay.
So
What
maybe,
time would the discussion be tomorrow, if at all there is?
so who all are there now? Like people who all are there now, can they just send me your details, and I think only it will be useful for our the people present now here. Or maybe I can give a mail to everyone, and yeah, who all can attend, and especially the people who are present today, it will be useful for them. Yeah. Maybe we can have the meeting at the same time tomorrow, 2:30. It will be for some half an hour, so you can wind up by 3 or 3:50.
Okay.
Yeah, that works.
Okay.
Thanks.
Yeah.
Cool, thanks.
Can you record tomorrow's session as well? I may not be able to make it.
Okay. Then. Bye, guys. Hope it was okay. Like
Thanks, bye.
too much.
Yeah, thanks, Shuaib.
Thank
Yeah.
you.